Hi, welcome back to the module Building Decision Trees from Scratch. In this lecture, we'll be learning about Gini impurity. In the last two lectures, we understood the theory behind decision trees. We also implemented decision tree from scratch, but the criteria that we were using whenever we decided to split a node into two or more branches was something called as information gain, which was based on a concept called entropy. So if you are not familiar with these concepts, don't worry, I'll be recapping this very briefly in today's lecture. However, I still recommend you to check out the previous lecture on decision trees from scratch, where we covered the theory and also we implemented decision tree, and also we discussed in detail about the physical interpretation of entropy. So let's have a brief recap first before going into the concept of Gini impurity. So imagine you have this data set which has three classes: cow, dog, and pig. So here the data points are being classified based on two features, height and weight. So you can see here that you can construct a decision tree to classify a new animal which is not part of this data set, and maybe the data corresponding to that new animal can be here. And if you build a decision tree using all the other data points, you can classify a new test data set into one of the three classes: cow, dog, or pig. The main idea here is that you start with a root node for this entire data set. So your root node looks like this. In the root node, there are 12 plus 10 plus 5, 27 data points. And what are those 27 data points? They are all these dots which corresponds to these many animals. So out of 27 animals that are part of the data set, 12 of them are cow. So this is cow. 5 of them are pig. And 10 of them are dogs. So you have 27 animals, and this is how the animal distribution looks like. So now this is the root node from where you start building the decision tree. So decision tree starts from one point, and it resembles a physical tree, but upside down. A physical tree grows from the root, goes upwards into branches, different branches. At the end of the branch, there is a leaf. In decision trees used in machine learning, you start from the root at the top, and then you go down in branches. At each branch, at the end of each branch, there will be another set of nodes. Some of those nodes will be where the branch terminates. So those are called leaf nodes, whereas some other nodes will be called as internal nodes, where there will be more branches starting from. And those internal nodes will have branches coming into it and branch going out of it. So not branches coming, one branch will be coming to it, and one or more branches can go out of it. So now the decision that we have to make at this root node, which can also be called as a parent node, so let me write it as parent, is what feature are we going to use to split, whether it is height or weight. So we discussed in the last lecture, consider two cases. In one case, we are deciding a feature of height and threshold of 90. So we ask the condition, is height greater than or equal to 90? If this condition is true, then all these data points actually follow that condition. They will go to the one side of the branch, to the right side of the branch. In fact, actually true is going to the left side. So maybe I can write it as less than or equal to. So if height is less than or equal to 90, if this condition is true, then all these animals satisfy this condition. They go to this true branch, true. And the rest of the animals go to the false branch. And what is the condition? Height less than or equal to 90. Now the question is, how did we figure out, or how do we know whether height is the best feature to use? Because when we use height as the feature, there are two children coming from this parent node. So this is child 1 and this is child 2. So from the parent, two children formed as nodes. In the child 1, there are 5 pigs and 10 dogs. And in child 2, there are 12 cows. Now, is this a better way to split the parent node? Or how about this? So same parent node, which is the root node consisting of 27 animals. Now, instead of splitting like this, let me delete these two. What if we split like this? What if we say instead of height greater than or equal to 90, can we say weight less than or equal to, say, 120? If we do that, then all these points will go into the true branch, which is this. In fact, here the condition should be weight greater than or equal to 120. So let me write it that way. Weight greater than or equal to 120. Actually, no, it is less than only. My bad. And weight less than or equal to 120 is true for all these data points. So this is the true branch. I think I made double mistake. If I want this to be the false branch and if I want this to be the true branch, it should not be less than, it should be greater than. I'm sorry for making the same mistake twice. But basically, if we use this as the criterion at the parent node, weight greater than or equal to 120, then for all these animals, which consists of 5 pigs, 1 dog and 3 cows, this condition is true. For the rest of the animals, which consist of 9 cows and 9 dogs, this condition is false, right? Now, the question that we wanted to answer was, which one is better? Is the left-hand side kind of splitting using height or the right-hand side kind of splitting using weight? Which of this is better? And we used the concept of entropy to answer this. So remember, we are still recapping the entropy and we have not entered the Gini entropy, the Gini impurity yet. So we measured something called as information gain, where what we said was, if the entropy reduction, the weighted entropy reduction is maximum for one kind of splitting, we will go with that. So the reduction in entropy is analogous to increase in information gain. So if entropy reduces by a factor of x, then information gain is by a factor of minus x. So if entropy is reducing, information is increasing, because entropy is a measure of randomness. So if things are not random, things are certain. If things are certain, it is information. So information gain is the opposite of entropy reduction. So we say that whatever split results in more entropy, more information gain, we go with that split. And we saw that in this case, the height-based splitting resulted in better entropy reduction or better information gain. And we calculated the entropy using this formula. The information gain was entropy of the parent minus the weighted entropy of the children. Now, don't worry with this formula if you don't exactly recall what we learned from the last lecture, or if you haven't gone through the last lecture altogether, don't worry. In the last part of this lecture, we will be comparing between Gini impurity and entropy. So there you will adequately kind of come back to calculating entropy from scratch. So don't worry about the mathematical implication yet. But this is the basic idea behind entropy. If a node has only one type of animal, for example, this child node 2 has only cow, and it means entropy is 0. And why is that? The formula for entropy is minus pi sigma log to the base 2 pi, and pi is the probability for something to be that class. Here only one of those classes are present, which means probability is 1, and logarithm of 1 is 0. So that's the reason why if you have only one class, it is called as a pure node whose entropy will be 0. Now, we use this pure node from the point of view of entropy, but today we will see why it is a pure node based on Gini impurity. If Gini impurity is absent, meaning if Gini impurity is 0, we will also see that it is a pure leaf. So that is what we are going to cover primarily in today's lecture. So let us get into the concept of Gini impurity. I have a question. So before entering into the discussion of Gini impurity, imagine you have 5 animals. Okay. So you have, or rather 5 shapes. You have 5 circles, 1, 2, 3, 4, 5. And you have 5 squares, 5 rectangles. Okay, so this is a collection of shapes. There are 10 shapes overall. And out of these 10 shapes, you have 5 rectangles and 5 squares. Now, my question is, if you were to randomly pick an element, how likely are you to be, and you are also not looking at what is the element, and you are saying, I'm going to randomly pick an element and that will be a circle, and then you make your random selection. How likely are you to be wrong? That is the question. Okay, so if I close my eyes and if I randomly select one of the elements, it may end up being a circle or it may end up being a rectangle with a 50% chance. And if I'm randomly choosing an element and labeling it randomly according to the distribution of label itself, I will be correct 50% of the times and I will be wrong 50% of the times. So Gini impurity is basically a measure of this, how wrong you will be if you were to randomly assign a label to a randomly chosen element, and this assignment of label depends on the probability distribution itself. And here, if 50% of the times, if I'm randomly guessing the shape, if I will be correct, and remaining 50% of the times I will be wrong, we can capture this using the parameter called Gini entropy. So the official definition of Gini entropy is exactly what I mentioned earlier. How often a randomly chosen element from a data set. So here is a data set. Okay, here is a data set. How often does a randomly chosen element, meaning how often does a randomly chosen shape, for example, this shape, will be incorrectly labeled if it was randomly labeled according to the distribution of labels. So now if it is randomly labeled according to the distribution, in the distribution, what are the two labels I have? There is a 50% chance that things are a circle, and there is a 50% chance that things are a square. So I'm randomly picking a shape and I'll randomly label it, and I'll be correct 50% of the times and I'll be wrong 50% of the times, because that's how the distribution of these shapes are right now. And that can be understood by the Gini impurity formula also. So the Gini impurity formula is 1 minus sigma I equal to 1 to C pi square. So pi is the probability of an individual class and C is the total number of classes. So in this example, how many classes are there? There are two classes, because one class is circles, the other class is rectangles. And here the Gini impurity would be Gini impurity equal to 1 minus and the probability for each class is 50%, 0.5. So it will be 1 minus 0.5 square for the first class, minus 0.5 square for the second class. So this will be 1 minus 1 by 4 minus 1 by 4 equal to 1 minus 1 by 2 equal to 0.5. So the Gini impurity, which is a measure of how often you will be wrong if you randomly select from this data set, and if you randomly label based on the probability distribution of the data set, that is the Gini impurity. And in this particular case, it is 0.5. So let me come back to the usage of Gini impurity in the decision trees, because that is what we care about, right? So Gini impurity, basically, we discussed there are pure leaves and impure leaves. Now imagine you have a leaf, a node rather, not leaf. Let me delete this. So imagine that you had a node which looked like this node. Maybe I can copy paste this. So imagine that you had this node. Here you have only one class. So C equal to 1 in this example, and Pi equal to P1 equal to 1. And what is Gini impurity in this case? Gini impurity equal to 1 minus sigma pi square, which is 1 minus 1 square equal to 0, right? And we also said that in this case, entropy is also 0, because entropy H equal to minus pi log to the base 2 of pi, sigma of this. In this case, it will be minus 1 times log to 1, and this is equal to 0, right? So entropy is 0, Gini impurity is also 0. And you remember in the last lecture, we discussed that this is a pure leaf, because there is no more splitting possible to this data set, because there is only one category of data. What is there to split if you have only one category of data, and if you are trying to classify data into, let's say, pig or dog or cow? Here there is no more split possible. So this is a pure leaf, and this purity is defined based on Gini impurity. If Gini impurity is non-existent, or if it is 0, it means it's a pure leaf. Otherwise, if Gini impurity is non-zero, if it is greater than 0, it's a impure leaf. Now imagine the worst possible leaf. A worst possible leaf will have a lot of data set, and every individual data set will be a separate data point. So imagine now this, maybe I can ungroup this somehow, and or let me delete this. So I just wanted to put some circles and different colors. So let's say this is yellow, and so imagine that you have a lot of data points. I'm going to copy paste so that I can multiply the number very fast. Okay, so imagine you have these many data points. here you have only one class. But now there are two classes possible, yellow and red. Now there are three classes possible, yellow, green, and red. Now there are four classes possible. Each of them, when I add more and more colors, you will see that more and more classes are possible in the data set. And that means the probability distribution for this data set will be, there will be a pi, there will be sigma pi square, where the individual pi becomes smaller and smaller and smaller. So now imagine that each of this color was a different color. Let me put white, let me put transparent, let me put dark blue, what else? This yellow, and this color, one more. This I can delete. So now if I were to say, what is the Gini impurity? There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There are 13 points and every point belongs to a different class based on color. Okay. And that means Pi equal to 1 by 13. And what happens to Gini impurity in this case? 1 minus sigma Pi square equal to 1 minus 1 by 13 sigma 1 by 13 the whole square. And how many times are you going to do this summation? You're going to do the summation 13 times. So this will be 1 minus 13 times 1 by 13 square equal to 1 minus 1 by 13 equal to 12 by 13. So the Gini impurity is approaching close to 1. And if we replace the Pi with 1 by 13 instead of that, what if it is 1 by n? Then it will be 1 minus 1 by n, because this 13 square and 13 square was cancelling, and this will be n minus 1 by n, right? If the probability distribution is equal. And what happens if n tends to infinity? What if there are large number of data points in a data set and every single class has only one data point associated with it? Then the Gini impurity will tend to 1, because the numerator will tend to infinity, denominator will also tend to infinity. So the maximum possible Gini impurity in the extreme limiting case where there is high entropy is Gini impurity tends to 1. Whereas the other extreme where all the data points belong to the same class, where the color of all these points are the same, if it is like this, then Gini impurity is 0, because there is only one class. So it's a pure leaf. The other one is an extremely impure leaf. Okay. So Gini impurity is very similar to entropy in some cases, but the computation is much more simpler because you don't have to calculate logarithm. You just need simple probability values. You're simply taking square, taking sum of that, and you are subtracting that from 1. So Gini impurity calculation is a lot more simpler than entropy, where entropy is like minus pi times sigma, minus sigma pi log to the base 2 pi, right? So a perfectly pure split, meaning if the data set belongs to only one class, Gini impurity is 0. But if something is not a pure split, when something is not a pure split, Gini impurity will be greater than 0 if it's a random split. And what if this randomness goes to the extreme, where there are infinite points and there is only one data point per class? Then the Gini impurity will be tending to 1, right? Okay. Now, I think this is a good time to get into a numerical example so that you can appreciate the difference between Gini impurity and entropy and how to calculate both of them numerically. So now this is also a good time where you can recap the calculation part of entropy if you have forgotten it from the last lecture. So imagine you have a data set at a particular node and you have 6 data points, and the feature that separates the data point is based on color. And you have 2 colors. One color is red and the other one is blue. And you have 2 labels. So you are doing a 2-class classification. Label is yes or no. And you can see that at the particular node where this data set is there, 2 of the red points are yes, 1 red point is no. 2 of the blue points are no, 1 blue point is yes. Now to calculate the feature that we are using, here we have only one feature, so we are left with no option. But if we had multiple features, what we would ideally do is what is the Gini impurity or what is the entropy which results when you use this feature to split the data set. So if you split the data set based on color, what is the resulting entropy of the children compared to the parent node? Or if it's Gini impurity, what is the resultant Gini impurity of the children compared to the parent node? So that is what we are trying to answer. So the steps involved are, first we initially calculate the original impurity or original entropy of the parent node or the root node. It may or may not be root node, by the way, because this data set could be a data that happened to be there at one specific node, which may not be the root node. It can be an intermediate node, internal node. Then what we do is, after we select the feature, here in this case only color, we split the data. Then after splitting the data, we calculate the Gini impurity of the individual children nodes. And then we calculate something called as weighted Gini impurity, because we have to compare the final weighted Gini impurity with the original Gini impurity. And if the impurity is decreasing, that means you are going in a generally better direction. And finally, you interpret the results saying, okay, Gini impurity of the original parent node was this much, the weighted Gini impurity of the children node are this much, which means you are generally going in a good direction. So let us calculate the initial node impurity. In the initial node impurity, first I have done a calculation of entropy. But actually you don't have to consider this right now, because I am anyway going to calculate the entropy for the children nodes at a later part of the lecture. So this table, you can forget about this table for a moment. So let's only focus on Gini impurity, right? So the original data set, so here I have denoted the data set by some symbols and colors. So if the label of the data set is yes, I denote it by a tick. If the color or the feature corresponding to that data point is red, it will be a red color tick. If the color is red and if the label is no, it will be a red color cross. If the color is blue and label is no, it will be blue cross. If it is color is blue but label is yes, it will be a blue tick, right? So these 6 points form the root node or the parent node. So there are 2 ticks, 2 red ticks, 1 blue tick, 2 blue cross, 1 red cross. And Gini impurity is equal to 1 minus sigma pi square. Now here is a question. What is the pi here? What are the classes here? Is it the color or is it yes or no? Because color means there are 2 colors, blue and red. Yes or no means there are again 2 classes. Either it is yes or it is no. Here we are looking at classifying things into labels. And what are the labels? Yes or no labels. It's not the color. Color is a feature. Color is not a label. So color is the input data and label is the output that we are trying to predict. So we have to calculate the probability square based on the label probability. So here we have 2 labels, yes or no. 3 data points out of 6 belong to yes, and 3 data points out of the 6 belong to no. So the P of yes is 3 by 6 equal to 0.5. P of no is 3 by 6 also, and that is also 0.5. So now this parent node, let me denote this as parent. This parent node will have a Gini impurity equal to 1 minus sigma pi square equal to 1 minus 0.5 square minus 0.5 square. So it will be 1 minus 1 by 4 minus 1 by 4, which is 1 minus 2 by 4 equal to 0.5. So the Gini impurity of this parent node is 0.5. Now we will split the data based on feature. We have only one feature, that is color. So when we split the data, the red color will go here. So here the condition is color equal to red, right? Something like this. And if the condition is true, this is the true branch. If condition is false, this is the false branch. And here 3 data points have red color and 3 other data points have blue color. Now let us again look at the probability for calculating the node level, children node level Gini impurity. So this is the child 1, this is the child 2, and this node was the parent, right? So first let us calculate the Gini impurity for the child 1. It is equal to 1 minus sigma pi square. And what is the pi? Probability for something to be yes in this child node and probability for the data to be no in the child node. There are 3 data points, 2 of them are yes and 1 is no. So P of yes is 2 by 3 and P of no is 1 by 3. So Gini impurity is 1 minus 2 by 3 square minus 1 by 3 square. So it is 1 minus 4 by 9 minus 1 by 9 equal to 1 minus 5 by 9, and the output is 4 by 9. So the Gini impurity of the first child is 4 by 9. What about the Gini impurity of the second child? The second child Gini impurity, it has 3 data points out of which 1 is a yes and 2 of them are no. And that means Gini impurity will be 1 minus sigma pi square. and that is equal to 1 minus 1 by 3 square minus 2 by 3 square equal to 1 minus 5 by 9 equal to 4 by 9. And if you notice, the Gini impurity for the child 1 and child 2 are both 4 by 9. Now we calculate something called as weighted Gini impurity. Weighted Gini impurity is nothing but you look at how many data points are there in each of the children, you calculate the Gini impurity of individual children, and then you do a weighted average. So here, parent has 6 data points, out of which 3 went to the child 1 and 3 went to child 2. So now the weighted Gini impurity is the, here I put H. H is entropy. Let me write this as Gini impurity instead of H. So this is technically not right, not correct. So Gini of child 1, and this is Gini impurity of child 2. So Gini impurity of child 1 is multiplied by number of data points in child 1 divided by the number of points in the parent. So that is the weight associated with that Gini impurity. The Gini impurity associated with child 2 is multiplied by number of data points in child 2 divided by number of points in the parent node. So the weighted impurity in this case will be equal to 4 by 9 because both nodes have equal number of data points 3 and 3, and both children nodes have the same Gini impurity 4 by 9. So the total weighted Gini impurity will also be 4 by 9, and 4 by 9 equal to 0.444. Now we can see what happened to the total Gini impurity when we went from the parent node to the child node. So parent node, if you remember, parent node had a Gini impurity of 0.5. This was the parent node, and we calculated it to have a Gini impurity of 0.5. But when it came to the child nodes or children, the Gini impurity, the weighted Gini impurity reduced to 0.444. It means that the leaves are getting a bit more purer. You will also see the exact same thing, not numbers, but exact same interpretation. If you look at entropy, you will see that the weighted entropy has reduced when it comes to the children compared to the parent node. And we will do that calculation in the next part. Now let us calculate the Gini impurity versus entropy for the exact same example. We are not going to change the example. So the example was parent node with 6 data points. 3 of them belong to yes, 3 of them belong to no. And the features were such that in the red color, 2 were yes and 1 was blue. In the blue color, 2 were no and 1 was, in the red color, 2 were yes and 1 was no. In the blue color, 2 were no and 1 was yes. So the initial node Gini impurity we already calculated to be 0.5, right? It was 1 minus sigma pi square, and pi was 1 by 2, basically 3 by 6, which is 1 by 2 because 3 data points are yes, 6 out of 6 data points, and 3 data points are no. So Gini impurity was straightforward. Now entropy is also straightforward if you know how to calculate. So it's minus pi sigma log 2 pi. Oh, this pi should be inside. Minus sigma pi times log to the base 2 of pi, where pi is again the probability for the data set to be in the class yes or class no, and that is 3 by 6, which is 1 by 2. So 1 by 2 log to the base 2 1 by 2 minus 1 by 2 log to the base 2 1 by 2, because 3 by 6 is equal to 1 by 2. And log to the base 2 of 1 by 2 is minus 1. So this will be minus of minus 1 by 2 minus minus 1 by 2. So it will be 1 by 2 plus 1 by 2 equal to 1. So entropy of the parent node is 1 and Gini impurity of the parent node is 0.5. Now let us come back to the splitting, which is the exact same step what we did in the previous example. So after splitting based on color, the left-hand side branch has 3 red points, out of which 2 are yes and 1 is no. So probability P of yes is 2 by 3, P of no is 1 by 3. So for this child, Gini impurity, we already calculated earlier it to be 4 by 9. But entropy would be minus sigma pi log to the base 2 of pi. So it will be 2 by 3 times log 2, 2 by 3, minus 1 by 3 times log 2, 1 by 3. So this you can calculate to be 0.918. So this is for the first child, whatever calculations you see here. Now for the second child, this guy, you have 3 data points. 2 of them are no and 1 of them is yes. So P of yes is 1 by 3 and P of no is 2 by 3. Again, Gini impurity we calculated to be exact same number 4 by 9. This was done in the previous step, but entropy is again minus minus sigma pi log pi. So it is minus 1 by 3 times log to the base 2 of 1 by 3 minus 2 by 3 times log to the base 2 of 2 by 3. So that is this calculation, which is also 0.918. So entropy of both children are the same, and Gini impurity of both children are also the same. Now, if we calculate the weighted Gini impurity, we did 3 by 6 because 3 out of 6 points belong to the first child, which has the Gini impurity of 4 by 9. Then 3 out of 6, remaining 3 out of 6 data points belong to the second child, which has a Gini impurity of 4 by 9. So if we do the weighted Gini impurity, the result turns out to be 4 by 9 itself, and that is 0.444. Similarly, for weighted entropy, 3 out of 6 data points belongs to the first child, which has a individual entropy of 0.918, and remaining 3 out of 6 data points belong to the second child, which has an individual entropy of 0.918 also, which means the weighted entropy is also 0.918. So now what we did was we were calculating, in the case of Gini impurity, we can calculate the reduction in Gini impurity. So while going from parent to children, the Gini impurity went from 0.5 to 0.444, whereas when we went from parent to children, the entropy went from 1 to 0.918. So both are useful metrics, both decreases when the splitting is good. But here we'll see which one to use and what is better. The only thing is Gini impurity is computationally a bit more efficient than entropy because logarithm is not used. So for most of the simple decision tree models or random forest models, you can actually use Gini impurity instead of entropy. But if you have a well-balanced data, if you don't have 100 data points in class 1 and only 25 data points in class 2, if that is not the case, you can go ahead with entropy. But if there is a lot of imbalance, maybe Gini impurity is a better measure. But other than that, these are both equally good, and entropy has a much more deeper connection with information theory, because when you take logarithm to the base 2, as we discussed in the previous lecture, we are essentially saying to the number of bits, we are essentially saying that, okay, to hold the information contained in this, these many bits are needed. So I'm not going into the details of that because that will consume another 10 minutes. But just understand that entropy is more deeply connected to information theory. Now it is a good time for us to start implementing the node splitting and Gini impurity from scratch. Please understand, we are not implementing the entire decision tree building from scratch here, because that we already did in the last lecture very well. Here we are just calculating the Gini entropy. Whatever numerical example we calculated above, the one with colors and yes or no, that same example we will try to implement using code. And we are basically doing a splitting of one node. We are not going to split the children node further, and we are not going to minimize the Gini impurity as much as possible. That's not what we are going to do here. And as usual, what I have done is I have already implemented the code, fixed some minor bugs, and the code is in a very, very, very good shape right now. So I have split the code into few different understandable chunks. So I will be walking you through those chunks first before actually coding. So it's not a long code at all. It's very short and very easy to understand. So first, let us walk you through this snippets of code, and then after that, let us implement this in Julia, in the Jupyter Notebook or Jupyter Lab environment. Okay, so let us get into coding. So firstly, we are implementing the code for calculating the Gini impurity, the simple formula that we were using, right? 1 minus sigma pi square. This block of code is to implement that in a systematic way. So first, the name of the function is Gini impurity, and we are passing the data. So let us just scroll down a little bit and just have a look at how the data set looks like. So data is a dictionary, which is a key value pair. So there are 6 key value pairs, and the key is color and value is label. And for each row in this dictionary, there is a color mapping to the label. So in the first data set, color is red and corresponding mapping label is yes. When the color is red in the second row, it is again yes. Third row, however, red is corresponding to no. Fourth, blue is corresponding to no. Fifth, blue is corresponding to no also. and last one blue is corresponding to yes. So this is our data set in the form of a dictionary. So just keep this in mind. And when we are calling Gini impurity, this data is what we are passing. This Gini impurity function is being called here, and we are passing the data. And let's go back to the Gini impurity function definition. So first we check the total length of the data. If the data is empty, we can simply say Gini impurity is 0 because there is no data to even cause impurity in the first place. So we simply return 0.0 as the impurity. But if that is not the case, meaning if the data is not empty, then we try to calculate the Gini impurity. So here there is something called as label counts. It's an empty variable. So we are defining a dictionary which maps from a string into an integer. It's an empty dictionary in the beginning. And let's start counting how many yeses and how many no's are there for every corresponding label, right? So for row in data, meaning the data, which was the dictionary, which had 6 rows. So we are now looping over each row one by one. Label equal to the label of that particular row. And the label of that particular row is the color, whether it is a red or blue, right? So the value of this label variable is either red or blue, depending on the row that we are looking at. And then here what we are doing is label counts of label. So this label counts is actually this dictionary, right? So this dictionary has a string, which is the label. And what is that value of that label? Value will be either red or blue, depending on what the value got stored here. And then here this get function is nothing but, you forget about this 0. Basically, this get function looks at a dictionary and the name of the dictionary is label count. And it looks at the corresponding label and it fetches the key corresponding to that label. So when this loop is starting, there is no key value pair inside the dictionary. It is an empty dictionary. So by default, initially when this get function is called, the 0 is the default value that it returns. Basically, that will assign to this label in the beginning a value of 0. So this get function's value will be 0. But then since the label, so label is nothing but the yes or no label, right? So if there is a yes present, then it will add 1 to the count. And the yes is present for what? Yes is present for a particular color, right? So we are, let me go back to the data. So label is the yes or no, and color is the red or blue. So we are counting the number of yeses corresponding to a particular color. In fact, not particular to a color. So basically this dictionary will look like this. So dictionary will have key value pairs. So the key will be yes or no. And the value will be number of times yes is occurring in this variable called data. And number of times yes is occurring is 3. So that is taken care of by this +1. So each time it sees a yes, it adds +1. So initially this will be 0, then it will be 1, 2, 3. No will be also the count of number of no's occurring in data. So this will be also 3. So finally, this Gini impurity function has this part of the code, which counts the number of occurrences of each label. So it counts that the label called yes is occurring 3 times and the label called no is also occurring 3 times. Then let's come to calculating the Gini impurity. So Gini impurity is originally assigned to be 1.0 because that is the maximum possible Gini impurity, because 1 minus sigma pi square. Pi in the worst case can be 1 by n, where n tends to infinity. So 1 minus pi square will become 1 minus sigma pi square will become 1 minus 1 by n, and that will be n minus 1 by n. So in the limiting case where n tends to infinity, Gini impurity will be close to 1. So we discussed that during the theory part. And if you remember from the last lecture, when we were calculating the entropy, we initiated the entropy value to be minus infinity, which is the worst possible entropy out there. I mean, no, not minus infinity is not the worst possible entropy. Infinity is the worst possible entropy. We define the information gain to be minus infinity. not the entropy. So the worst possible information gain is minus infinity. So we started with that here. We are starting with the worst possible Gini impurity. And then Gini impurity is equal to 1 minus sigma pi square. And so if initial value is 1, then this will be 1 minus probability square of whatever is the probability for that particular label. So values in label counts means what will be the count going from, it will start from 1, it will go all the way till 2, because the values in label counts are only this. Label counts is a dictionary, and it has only 2 values. The first value is 3, and second value is also 3. So the value of the count will be 3 in the first iteration. In the second iteration also, value of the count will be 3. Total is how much? Total is calculated over here. Total equal to length of data, and length of data is nothing but the number of rows in the original dictionary which we are passing into Gini impurity, that is 6. So 3 by 2. So Gini impurity, this will, after running this 2 times, in the first loop, Gini will become 1 minus 3 by 6 square. In the second loop, it will become 1 minus 3 by 6 square minus 3 by 6 square, right? So this will be the final Gini impurity that this function is returning. Now, a code for splitting the data, because after calculating the initial Gini impurity, we are going to split the data and then again calculate the weighted Gini impurity. So for splitting the data, we have the feature that we are going to split, and we have the value that we are going to use as the threshold. So value in our case will be red or blue, right? We will either say color equal to red, and feature is color. Feature is color and value is red or blue. We have only one feature but 2 colors. And data is the entire dictionary which had 6 rows, 1, 2, 3, 4, 5, 6, where color was mapped to a label called yes or no. So to the left branch and right branch, we see what all data points are going. So to the left branch, all those rows, where row is each row belonging to the data set and data is the dictionary. If the value of the feature equal to red, then red or blue, depending on what we are passing here. If the value equal to whatever we are passing, then the condition is true, then it goes to the left branch. If value is not, if the value of the feature is not equal to the value that we are passing into this function, then the condition is falsified, so it goes into the right branch. And then we pass 2 nodes, the left node and right node, and you should know that this left node is the child 1 and the right node is the child 2, right? So basically this left node will contain 3 rows from the original dictionary, and this right node should contain other 3 rows from the same dictionary. So these are 2 children and they are both dictionaries. Now weighted Gini impurity calculation. So in the weighted Gini impurity calculation, we are passing the original data set, which is the all the 6 rows. Then we are passing the splits, and if you look at the splits is whatever we are returning from this function. So let's look at where this function split data is being called. The function split data is being called here, and into that we are passing the data. We are passing color as the feature, and we are saying, we are comparing whether the color is red or not. And this split data, we have red split and blue split. Now, if you look at the part where this weighted Gini impurity function is being called, which is weighted Gini is being called, we are passing the original dictionary, and into one single array, we are passing the red split and blue split. These are the 2 children. So here, if we go to weighted Gini, this splits, the first element of the split is the left-hand side node, which is the child 1. The second element of the splits is the right-hand side node, which is the child 2. So for splits means this loop will first consider the first child, second consider the second child. So the weighted Gini impurity is initially assigned to be 0. Total means it's the length of data, it's the number of data points, which is 6. So split Gini equal to Gini impurity of split. And here what we are doing is we are calculating the Gini impurity of the first child. So when this for loop is running for the first time, it calculates the Gini impurity of the first child, and that is stored here. And weighted Gini equal to weighted Gini plus this is the weighting factor. So basically the weighted Gini weighted equal to number of data points in child 1 divided by n total times Gini of child 1 plus number of data points in child 2 divided by n total times Gini of child 2, right? So you can recursively, you can do this over loops by saying you initialize the weighted Gini impurity to be 0. Then to that number, you add this guy. Then to this whole thing, you add this. So that is what that's why you have a plus minus plus equal to here. So weighted Gini impurity in the second loop equal to whatever weighted Gini impurity was from the previous loop plus this additional length of the split, which is the number of data points in child 2 divided by total means the total number of data points in the original dictionary times split Gini. In the second iteration, it will be the Gini impurity of the second child. And then we are passing this weighted Gini impurity, which is a single number, as the output of the function. So we are returning that actually. Now, example usage, we already discussed about the data. Then after defining the data, we call the Gini impurity function for calculating the Gini impurity of the entire data set at the root node or at the parent node. So initial Gini impurity is whatever Gini impurity is there for the initial data set. Then we split. So the red split and blue split is nothing but splitting into the left branch and right branch. So these are the two children nodes. So for that, we call the split data function and we pass the original data set, which is the entire dictionary. We pass the feature, which is color, and we pass the threshold value, for which we are using a specific value of the feature, which is red. We could have used blue also, no problem. And then we just print the child 1 and child 2. After that, we calculate the weighted Gini entropy using the original dataset. This original dataset is only used for calculating the total number of data points. Instead of passing this dataset, we could also simply pass the length of the dataset. That would have also been fine. And then in the red split and blue split, we are passing it as a single variable. And red split is the child 1, blue split is the child 2. And then we get the split Gini is the variable that stores the weighted Gini impurity, and we simply print it. So this is the entire code, and I hope you understand it fully. It's very, very straightforward. And now we can implement this in Jupyter Notebook. So as usual, let's open terminal. And inside the terminal, we will type Jupyter Notebook. And this should open as a local host in our Chrome. And then we will be opening Jupyter Lab, and that's where we will be coding. So of course, you need Julia, you need Jupyter Notebook, and you need Jupyter Jupyter for Julia, 3 packages. And if you don't know how to do this, you go back to the first lecture in this series. I have explained in detail. It hardly takes you 5 minutes. So if you haven't done that, just go ahead and do it. But assuming you have done it already, let me open the Jupyter Lab. So click View, open Jupyter Lab. I can just close this. Now in the Jupyter Lab, obviously we need a new notebook. This notebook by default will be Python. I'm going to change this to Julia 1.1, 1.1. And maybe this I can rename as right click, rename Gini impurity. Fairly straightforward. Now we can just start fetching the code and we can just put it. So first, Gini impurity, defining the Gini impurity function for calculating Gini impurity of a given node. So I'm copy pasting that. It should not output anything because we are simply defining the function. There is nothing, we are not calling the function yet. It's just the function definition. Then the function for splitting the given node into right hand side and left hand side branch, basically true or false branch. So that is this function split data. We are not calling it yet. Then after splitting the data, we have 2 children and we have to calculate the weighted Gini entropy of those 2 children. That is what this guy is doing. So Gini entropy is calculated by the first function, but this guy just does the weighted average. And after this, we define the data set and we simply call these 3 functions. So I already explained this in so much detail that I don't have to go through it again right now. It doesn't make any sense. But let me just run this to you and show what's happening. So initial Gini impurity turns out to be 0.5. And can we go back to our original data set in the theory part? If you remember, the parent had a Gini impurity of 0.5. And that is exactly what we have calculated here using code, 0.5. And then you have red split and blue split. So red split is this branch, in the red split, you have 2 yes and 1 no, right? So is that what we have here? So the red is the color, the label is yes. Red is the color, label is yes. Red is the color, label is no. So you have 2 yes and 1 no in the left-hand side red branch. In the right-hand side branch, which corresponds to blue, you have 1 yes and 2 no's. So you have, so this is the blue split branch. So you have blue corresponding to no, another blue corresponding to no, and another blue corresponding to yes. So you have 2 no and 1 yes. And we also had calculated that the Gini impurity, weighted Gini impurity after splitting, Gini weighted was 0.444. And you can see that here also in the code, we are getting exactly same thing. Gini impurity after splitting is 0.444. So this is a fairly straightforward implementation of Gini impurity. Now we can use this wherever we want. In the building of decision tree from scratch, we can use the same thing. But I think this is a very good place for us to conclude this lecture. We learned about Gini impurity, which is a very common and very important concept within decision trees. We also kind of built a decision tree from scratch, although we did not build the entire tree. We just built it for two branches coming from one node. And we discussed the theoretical aspects about Gini impurity and entropy. And also we implemented all of this from scratch in Julia code. So we can wind up this lecture here. And as usual, I really appreciate you for coming all the way till this part in this course of, in this series of lectures. I'm sure you are enjoying it so much, otherwise you would not reach here. So I really appreciate you for taking the effort and taking the time. So you should feel very good about it. I'm also feeling very good about it. And we'll meet again in the next lecture. Take care until then. Bye.